The nature of dark matter is one of the most challenging mysteries of modern physics. Astrophysical observations suggest that dark matter constitutes approximately 85% of the matter in the universe, yet its properties remain elusive. One intriguing possibility is that dark matter could be quantum in nature, governed by the principles of quantum mechanics. This video will explore this hypothesis in detail, discussing the current understanding of dark matter, the evidence for its quantum nature, and the challenges and implications of such a scenario. To start, it is useful to review the current understanding of dark matter. Observations of galactic rotation curves, gravitational lensing, and the cosmic microwave background have all provided compelling evidence for the existence of dark matter, which appears to be distributed throughout the universe in a diffuse, invisible form. Despite intensive efforts to detect dark matter particles, however, no direct evidence has yet been found. This has led many physicists to search for alternative explanations, including the possibility that dark matter could be quantum in nature. The idea of quantum dark matter is based on the notion that the particles that make up dark matter could behave differently from ordinary matter in certain ways. In particular, they could interact much more weakly with ordinary matter than other particles, making them very difficult to detect. Additionally, they could exist in a superposition of states, meaning that their position and momentum would be uncertain until observed. This would make them difficult to observe directly, but would also mean that they could have very different behavior from ordinary matter on cosmological scales. There is some evidence to suggest that dark matter could be quantum in nature. For instance, simulations of dark matter behavior based on quantum mechanical principles have produced results that are consistent with observations of galactic rotation curves and gravitational lensing. This could indicate that the quantum behavior of dark matter plays an important role in shaping the large-scale structure of the universe. Another piece of evidence for quantum dark matter comes from the observed density and distribution of dark matter in the universe. These properties appear to be consistent with the distribution of quantum fluctuations that would be expected to arise from inflationary cosmology. This could suggest that dark matter is a manifestation of these fluctuations, and is therefore inherently quantum in nature. There are also many theoretical arguments in favor of the quantum dark matter hypothesis. For instance, some models of particle physics predict the existence of weakly interacting massive particles, WIMPs, that could serve as dark matter candidates. These particles could have very different behavior from ordinary matter on quantum scales, making them difficult to detect with current technology. Additionally, some models of higher dimensional physics predict the existence of dark matter fields that could have very different properties from ordinary matter on cosmological scales. Despite these pieces of evidence in favor of the quantum dark matter hypothesis, there are also significant challenges to its viability. One of the biggest challenges is that it is very difficult to detect quantum dark matter directly. Even if dark matter particles are weakly interacting, they should still interact with normal matter in some way, and this interaction could in principle be detected. However, the strength of this interaction is predicted to be very small, which makes detection challenging. Another challenge is that it is difficult to reconcile the quantum behavior of dark matter with the observed large-scale structure of the universe. According to quantum mechanics, the behavior of particles on large scales should be affected by quantum entanglement, meaning that the behavior of one particle is influenced by the behavior of another. However, this effect is predicted to be very small for dark matter particles, which means that it is difficult to explain the observed clustering and distribution of dark matter in the universe. Finally, there are also broader implications of the quantum dark matter hypothesis for our understanding of physics. If dark matter is indeed quantum in nature, it could have significant implications for our understanding of the fundamental laws of physics. For instance, it could suggest that there are additional, undiscovered fundamental particles and forces that govern the behavior of dark matter. It could also lead to a rethinking of our understanding of gravity, since the behavior of quantum particles on large scales could be influenced by gravitational forces in ways that are not yet fully understood. In conclusion, the question of whether dark matter could be quantum in nature remains an intriguing possibility in the field of physics. While there are some pieces of evidence in favor of this hypothesis, there are also many challenges that must be overcome in order to fully understand the behavior and properties of dark matter particles. Ultimately, the resolution of this mystery will require a better understanding